Welcome to RF and millimeter wave IC design class. This is your lecture number 4 of unit 3, and we are discussing about LNA topologies. So in the previous classes, we covered a few basic topologies, started with a common source with a resistive load, found out that resistive loads are not suitable for RF application, so we moved to inductive load, and yeah, so we moved to inductive load. With that, we verified the impedance input matching. So input matching was 50 ohms of input matching was possible, but one problem what we saw there is, even though we did not see that extensively, at some frequencies, this can give some negative impedance that leads to instability, and that is basically because of the interaction from the input to output through through the capacitance of CF. So that leads to this negative impedance at some point. So that means the circuit will be unstable. So we are not able to use that inductive load for any practical applications. Then we saw another type of CS with resistive feedback. So the whole idea of making it resistive feedback is just to make sure that the input matching is possible through that. So by adding a feedback resistance there, we saw that the input matching is possible of 50 ohm, because that is by neglecting all the other non-idealities. We also verified the noise figure, and noise figure is showing more than 3 dB. So then we are looking at other architectures, and with that we started with common gate amplifier. The load is inductive because anyway we have discussed about resistive load before, so the load is inductive. And there we saw that the input matching, since it is common gate, the inherent advantage or like in the inherent feature of common gate is it will have a low input impedance. So with that, it was easy to match to the input impedance or input matching requirement. And when we looked at the noise figure, it is coming very close to 3 dB or more than 3 dB. So that is a point where we come to common source again with the degeneration. Again, I think I mentioned that we will go back to common gate and we will do some modifications here so that we can make this configuration also a useful one. Then we started with the common source, the degeneration, and because in the beginning when we discussed, we said that the whole idea of using a low noise amplifier is to add minimum noise to the system, because the circuit itself will add little noise to the system. And for that, if a circuit or a system need to have less noise, then the number of resistive components what we can use, or we can avoid the resistive components, thereby eliminating the resistive noise coming from the resistor. So with that, we looked at a common source with a degeneration impedance. We did not put specifically a resistance or some capacitance there. We looked at this configuration. We did not consider the load part. Anyway, we know that load can be an inductive load. So at the input side, we observed that the input impedance is coming as ZS plus 1 by SCGS plus GMZS by SCGS. That is a point where we stopped our discussion, and I think I asked you to verify this impedance by substituting either a resistance or a capacitance or a inductance. So that exercise we will do today. So this is the impedance what we got from the discussion on CS with degeneration. And let us start this looking at the input impedance one by one. So the first case what we will consider is, I'll substitute this ZS as a resistance. So if I'm, but even before substituting a resistance there, we know that resistance will definitely add noise. But before dismissing that, or before just ignoring that, we'll just consider that and see what is the effect, and then we will talk about that. So now, if your source impedance, if what you are substituting is a resistance, the input impedance is, hope you are with me. Can I get some response in the chat? Since I started late, I was just going like that.
Yes, so
All right, yeah. Please respond in the chat so that I can see a response from everyone. Yes, thank you. So Zin can be written as Rs plus 1 by S CGS plus GM into, in place of ZS you have Rs again divided by S into CGS. So this is what we have as the input impedance when you substitute. Yeah, thank you for the response. So when you substitute for resistance, this will be the input impedance. Now, if I rearrange this in a little more better way, because the second and third terms have the same denominator, so I can write this as 1 plus GMRS divided by S into CGS. This is the input impedance, RS plus 1 plus GMRS by S into CGS, right? So if I look at this, what you can see is RS is the resistance what we added, and the second term, if you look at the second term, we can see that this gives some kind of a, this is some kind of a capacitive reactance, right? Because the form is 1 by S into C, or you can even think of this as, if I rewrite in this form, I can write this as 1 by SCGS divided by 1 plus GMRS. So this can be thought of having we are having a capacitance, or if I draw the input impedance, or if I look at the input impedance, it is something like this. There is a resistance of value RS in series with the capacitance, where the equivalent capacitance of the circuit. So this is what your input impedance is now looking like. There is a resistance and a capacitor in series. What is the equivalent, what is the value of the capacitance? The capacitance value is the CGS value divided by 1 plus GM into RS. This is the value. But unfortunately, we know that when you add a resistance, that is going to add noise to the system. So adding a physical resistance, so adding a physical resistance of RS, physical resistor RS will add noise to the system. And and the another thing is, we have also option actually to try out other elements without noise. So with this, we will conclude that, okay, we cannot use source degeneration as a resistance, because that is directly adding to noise. And with that, we will actually move to the next form of the next element what we can substitute there. I hope this is clear. So what we will do here is we will go for 1 by SCS. So ZS, I'll substitute a capacitance. That means I'm physically adding a capacitor at the source node, so that I'll see what kind of input impedance I'm getting, and is that possible to match with the conditions for the noise figure. So that is the case. Now if I substitute back for input impedance, the first term is ZS. So in place of ZS, what I have is 1 by S into CS, plus the second term what I have is 1 by S into CGS, and third term what I have is GM ZS by S into CGS. So I'll write it as GM, and ZS is 1 by SCS, so that I'll get as S square into CGS into CS. This is the input impedance expression if you substitute a capacitor at the source node of the common source of the regeneration, like the common source transistor. Now, if I look at the impedance, so whatever I have written is actually the function of S. So if I write in form of if I write S as j omega, so my intention is to just verify whether am I getting some negative resistance component, because we know that negative resistance ultimately leads to instability of the system. So this is 1 by j omega into CGS plus GM. It is not plus because there is a term of S square. So I have to put a minus sign here and divide by omega square into CGS into CS. This is what we will get the input impedance. Now, if I write this in a better form, I'll take j omega common here. Then I have 1 by CS plus 1 by CGS, which can be written as CS plus CGS divided by CS into CGS. This is the form what I can write by combining the first two components. And the second component is minus GM divided by omega square into CGS into CS, which is the input impedance now when you add a capacitor at the source node. So again, if you look at the input impedance in form of its equivalent components, you can see that there is a resistance here. The resistance value is minus GM divided by omega square into CGS into CS. Along with that, you have a capacitance, and the equivalent capacitance value is equal to CS plus CGS. Sorry, yeah, equivalent capacitance value will be reciprocal of the CS into CGS divided by CS plus CGS. This is the input impedance of the circuit if you have a capacitor at the source node, right? But again, from here, we can see that there is a negative resistance component here. So that negative resistance, in one way or other way, it will definitely go. It will definitely affect the stability, or this negative resistance will definitely leads to oscillations in the circuit. We will see little more about this negative resistance in the case of oscillators when we start. And there, what we do is, whenever such negative resistance comes, we will try to compensate, or we will try to so the idea in the case of in the oscillators is, maybe I'll explain that when we start oscillators. All right, so this will lead to oscillation, or in turn I can say that this will lead to instability of the circuit. So for now, take it as, if there is a negative resistance, that will lead to instability. And how this is useful in the case of oscillators, we will see. All right, yeah. So this is what the second case. So when you substitute a capacitor, you are getting an input impedance without any physical resistance, but that can lead to instability of the circuit. So in that case, the only one element we have now is the third element. Let us try that third element, and that third element is Zs, is an inductance. So I'll write it as S into Ls. Now, when I substitute in the input impedance formula, I'll get it as S into Ls plus 1 by S into CGS plus Gm into Ls divided by CGS, because one S and in the numerator and denominator will get cancelled. So this is the input impedance formula. Now, again, if I try to combine here, or if I look at the components, I'll just reverse the order. I'll write it as Gm into Ls divided by CGS plus S into Ls plus 1 by S into CGS. This is the input impedance, right? Now here I am not able to combine any term, because if you look at the first term is not a reactance term, it is a resistance term. So I'll call this as resistance. And one more important thing here is, we are getting a resistance whose value is Gm into Ls by CGS, and which is a positive resistance. It is not a negative resistance. So since this is a positive resistance term, what we can say is this will not lead to instability, right? So what we are trying to do here for the past 2-3 pages, what I was doing is, I am trying to find the input impedance. And what is our need? Our need is to have an input impedance, or we should be able to match the input impedance to a purely resistive impedance of 50 ohm. That is our need. But in the first case and second case, we found that there are some difficulty. But in this case, when you substitute an inductance at the source node, what we saw is we have a resistive element, but it is not a physical resistance. The resistance component we obtain with the help of the capacitance and the inductance component. And then there is a purely, then there is an inductance term. This is an inductance term, and then you have a purely capacitance term, right? So, but this looks attractive. Why? Because if you look at the input impedance, you have a resistance term, then you have an inductance term, and then you have a capacitance term. This is how your input impedance is actually now looking like. So what is this resistance? It is GmLs by CGS, and this is capacitance of the value CGS and inductance of value Ls. Now, so what is the beauty of this circuit? If you look at the circuit, we did not add any physical resistance, but even without adding a physical resistance, we are getting a resistive component, and that is without any noise, right? So without adding a physical resistance, we are getting a resistance component, getting a resistive component. Right. So that is actually the beauty of adding an inductance at the source of a common source transistor. Now, yeah. So again, are you guys with me? Are you getting what I am trying to say here? Any questions? If you have questions, can you please post in the chat, so that we'll move forward, and we'll see how input matching is possible here. Is this clear? Can I get a response in the chat? All right. Okay. So any can I get few more response? All right. Yeah. Thank you. So without adding a physical resistance, we are getting a resistive component. Now, what should we do? Uh, so we know that since you have an R, L, and C, so what I need is the input impedance should be matched to 50 ohm. So what for that, what I can do? Input impedance here is GM LS by CGS, or like how will you define the unity gain frequency? We'll define this as GM by CGS plus CGD. I hope this is familiar for you. CGS plus CGD. This is what is the transit frequency of a transistor. So if I neglect the CGD component as small compared to CGS, if the CGD component is small, I can actually approximate this as GM by CGS. Right. This is just to write the equation I'm using. No need to approximate. If you have a sufficient value, no need to approximate. But I'm just writing omega t can be also written as Gm by Cgs. In that case, I can equate this into omega t into Ls. So the resistance component what we have here is equal to omega t into Ls. And uh, what is our need here? I need to equate this resistance into a 50 ohm pure resistance. So omega t Ls should be equal to 50 ohm. Right. So, but what is the problem here? You have R, L, and C, and your R should be equal to 50 ohm. What can we do with the reactive components L and C? The reactive components can be eliminated. So, reactive components, how can I eliminate reactive components? Just to operate at the resonant frequency. So, reactive components can be eliminated or it will be eliminated at a particular frequency. And what will be that frequency? I can write that frequency as 1 by 2 pi into root of LC, where L is Ls and C is CGS, right? So at this particular frequency, at this resonant frequency, L and C, the effect of L and C will be neutralized, and what you will see at the input will be a pure resistance whose value can be value is determined by omega t into Ls. Is this clear? Is this clear what I'm saying? So L and C at resonant frequency, L and C will definitely give you a zero, or the L and C effect will be neutralized, and what you will see will be a purely resistive component. Is this clear? All right. Okay. Yeah. So now the two things what we have seen here is, one is input matching. So I need to have input matching, and for that input matching, omega t into Ls should be equal to 50 ohms. Right. This is for input matching. What is the second thing? Input can be matched to 50 ohm with omega t Ls by setting omega t into Ls, and that can happen only at only if you operate the LC at resonance. Right. So for this, we need to operate LC at its resonant frequency. What is that frequency? Here it is 1 by 2 pi into root Ls into CGS, right? Now, do you see any bottleneck here, or do you see any problem with this setup? Because if you want to have input matching, you need to match omega t into Ls equal to 50, right? And at the same time, whenever you match omega t into Ls as 50, you can get the input, or you can match it to 50 ohm only if you cancel out the effect of L and C. So do you see any problem here, or any difficulty here? Input matching should be done, and that should happen. Input matching should be also okay. So I'll explain. I'll ask in this way. So if I want to do input matching, okay, low GM value, but that should be fine, Pratap. Why low GM value is a problem? F naught is really large, insufficient gain. Need not be always, because yeah, we cannot say that a low GM will always lead to a low value, because the gain what we are looking here is not a huge value like an op amp open loop gain. Typically we will look for a gain of around 15 dB to 20 dB, 25 dB, that's it. So I think with the GM value, with the low GM value, it's also we can actually reach to that gain. I don't think that is an issue here. Yeah, F naught is really large. How will you say that F naught is really large? Yeah, that depends on LS and CGS component. So what I'm asking, my question here is, as a designer, are you seeing any difficulty in input matching, for input matching, any difficulty? Any thoughts on that? All right. So let me ask in this way. So if you want to match the input impedance to 50 ohm, what freedom or what component will you vary? Yes, Lalit, I think you got the answer. Making sure resistances are same and F naught is also satisfied is hard. Yeah, my question is why that is hard? Can't vary omega t so much, only LS need to vary. Yes, Kashish, yes. So omega t, yeah. So coming to the answer for that, omega t is not fixed by us. It is actually the limit of omega t depends on what technology we use. So even before we start our design, we will know that what will be the omega t, or we should actually check what is the omega t of that particular technology node. All right. So omega t is not in our hands because that purely depends on the parasitic capacitance, CGS and CGD. So those values also we do not have any control over that. So the only thing is what we can do is we can actually check the omega t or the transit frequency of the technology what we use. So that means that we cannot vary omega t in any way, right? So if I want to do input matching, the only possibility is this can be variable. This omega t I can change. So depending on the value of omega t, depending on the value of omega t, I can choose an LS such that omega t into LS can be made equal to 50 ohm. I think that point should be clear now. So omega t we do not have any control. So only one degree of freedom we have here, and that is LS. By choosing an appropriate value of LS, you can make omega t into LS equal to 50. Right. If that is clear, now tell me what is the issue here. So in order to do input matching, we will definitely choose a specific value of LS. So that means I have chosen the value of LS by setting the input matching condition. And now when I substitute that LS here, it should operate at, or the LC should be at resonance, or by choosing an LS value for input matching is setting the LS value such that, all right, yeah, LS has to vary such that, yes, 50 also, and frequency then needs to be at resonance. Yes, that is the point. Yes, very good. Yes, I think I was actually elaborating and making, maybe I'm confusing. So the point here is I have only one degree of freedom. So this is the only degree of freedom what is available to me, only degree of freedom. And with this, with the LS value, I need to choose, or I need to do two things. One is I need to do input matching, and another thing is I need to operate the LC at resonance, and which is difficult. Right. So I have only one degree of freedom and I have two conditions to satisfy, and which is not possible. So what do you think, what can be done at this point, so that, or what should be done at this point in order to come out of this difficulty? So we have two conditions to be satisfied and we have only one degree of freedom. That means we have to have one more degree of freedom, right? So what we need to do at this point is we need to add another degree of freedom. Right. That means if adding a capacitance, actually not. So did you mean adding a capacitance somewhere, where adding a C in parallel with the inductance? You meant to say that you want to add a C parallel to the inductance of LS? I don't know whether it will help exactly, because there are two things. So that can be varied to change F naught. So now the difficulty is if you add a capacitance parallel with LS, You have another capacitance which is CGS. So CGS and L, or the total capacitance and L, should resonate, right? So I didn't try that, but I don't think that is a viable option. So what we can do is, so I'm just straight away I'm giving you a solution, but you can come up with, you can check out, are there any other possibility actually to introduce one more degree of freedom to set this or to fix this issue. So the possible solution here suggested is, we can actually add one inductor at the gate. You can add one inductor at the gate. It is something like this. So you have a transistor here, sorry. Yeah, so we have the transistor here, and now the condition is like this. We added an inductance Ls here in series, and we have the parasitic element CGS here in parallel. So we have CGS. This is the CGS value, and what I was checking is, looking from this side, I need to have an input impedance which should be of 50 ohm, and at the same time it should operate at resonance, but that is not possible. So the solution what proposed here is, we can actually add an inductance here in series to the gate as LG. So the beauty of adding an inductance to the LG will actually also ease a lot in analysis. Why? Because previously we wrote the input impedance as some value. What is the input impedance value? We had it as omega t into Ls, which is, I'll write from here, yeah, Gm into Ls by CGS plus this component, right? So let me write it like this, Gm into Ls by CGS plus j omega into Ls plus 1 by j omega into CGS. This was the input impedance when you had added only Ls. But now if you add an inductance at the gate, the input impedance will just modify as, or you will have one more additional term here as j omega into Lg, or you can write the total input impedance component as omega t into Ls plus j omega into Ls plus Lg plus 1 by j omega into CGS, right? So I will not say there are no other solutions, but this is the best solution what we can get. So now what we can do here is, you have omega t into Ls, so this can be, or using Ls you can actually match this to 50 ohm or whatever is the impedance what we need. And so now I need to also operate the L and C in resonance. So what I can do, I can directly go and vary. I have an option here to vary Lg such that you can actually make these two terms to operate at resonance, right? So input matching is possible. I can resonate the LC component also. So I have two conditions here. I have 2 degrees of freedom, and that is how we have actually come up with this form of or this part of the architecture. So if I continue to, I hope this is clear. So I haven't discussed any other options. I'm not telling that there are other options, but this is the best option what we have, right? Other things, even if you have some more ideas, please share. We'll just see how that is possible, right? So with this, what I'm doing is, so I have made input matching condition possible by suitably adding components here. So if I look at the complete structure, now what I have is a transistor whose inductance is, its source is degenerated with an inductance of Ls, and you have gate inductance Lg, and this is the point where you provide V input. And so now I need to look at the output side. So output side, what we can do is, we can actually add another inductance to get the V out, and this is usually called as LD. So this is the structure, or this is how we have the common source degeneration. But I'm not telling this is the ultimate, or this is free of all the problems. We still have a little more problems, or we can actually make the circuit more, we can improve this existing circuit itself. So one thing what we can suggest here is, So this is your simple, not simple, this is CS amplifier with inductive degeneration. The CS amplifier with inductive degeneration, and this is a suitable candidate for a low noise amplifier because we haven't added any inductor, any resistance, physical resistance, but still we were able to match with the purely resistive impedance of 50 ohm, and we do have inductance here, and thereby we are not adding additional any noise. But another thing observed with the circuit is we know that there is a CGD capacitance present here between the input and between the gate and drain. And if you look at the structure, the input and the output node can interact through this CGD capacitance. So if you remember when I started the first architecture, even there I mentioned about the negative resistance which is coming up. So here this CGD can result in some form of instability. So generally we have two ways to come out of this instability. So the problem here is what I'm citing here is since the input and output are directly connected through this capacitance CGD, this can lead to some cause of some form of negative resistance, or or this can actually lead to instability. So we need to do certain things, or we need to adopt suitable techniques so that there will not be direct interaction between the input and output port. That means to improve stability, there are two things what we can do. One is since you have a CGD capacitance interacting between or connected between, sitting between the input and output, we can eliminate this by suitably adding an inductance here, but which is not practically viable or feasible always, because you may need to have a large inductance value. So the first thing is, in order to eliminate that, we can actually try for a resonance circuit to neutralize the effect of CGD. But that may result in a larger, but this may result in large inductance value. So including a large inductance in the layout itself, it will take like suitable, it will take some amount of area. So that is not a very optimized solution. But the good solution here is, in order to reduce the interaction between input and output port, what we can do is actually we can add cascoding, or we can add cascode transistors here. This is a simple way by which I am actually modifying this architecture. So what I am doing here is I have the inductance load, and I will be adding one transistor here, and that is a cascode transistor. The aim of or the role of that cascode transistor is to eliminate direct interaction between the input and output. Thereby we can eliminate, or we can make the circuit more stable. So this is my input point, this is LG, this is LS, this is input transistor M1, this is cascode transistor M2 with that need to be suitably biased, and this is the output point Vout, and this is our LD transistor. Again, one more thing here is, this node will definitely have a capacitance. So that capacitance will be the internal capacitance of the transistors, and even the input capacitance of the next stage. So when you operate, choose LD such that LD into CL will again operate in resonance. So this is a kind of final circuit what I can say, and this circuit is called as common source Cascode LNA with inductive degeneration. Right. So what I did is, soon after finding the suitable component to be added at the source point, we verified for input matching. We also added a provision, or added one more degree of freedom to make the circuit operate at resonance. After that, what I was telling is, in most of the circuits, if there is an interaction, if there is a direct way to interact between input and output, that was leading to instability. Especially CGD component, if present, or if the input and output are at the gate and drain of the same transistor, at some frequency that was giving some negative resistance and that was leading to instability. So what I was telling two techniques to improve stability. One is by adding a inductance in parallel to the capacitance, but the value of inductance may be large, which can result in the value of inductance will be large, which can result in actually a large layout area. So one feasible option is to add a cascode transistor such that we can eliminate the eliminate the interactions directly. Yes, I think Lalit have a question, but won't the operating voltages shift by a large amount by cascoding? Yeah. So what I need to do here is, and what about the headroom? Yes. So we definitely we need to look at the headroom, but the only problem, because you know that the load you have is an LD, there is an inductance there, so there is no DC drop across it. Again, you have an inductance LS at the source point. So only thing is we are actually compromising, or we are actually giving little headroom, or the headroom is consumed a bit because of the addition of these transistors. And suitably by fixing the VD SAT, or by suitably choosing an overdrive voltage, I think that that will not cause any issue here, because we are actually not looking for a very large yeah, we are looking for a gain which varies from some 15 to 30 dB, but this additional transistor is not going to affect you in any way. And more than that, this additional transistor is actually giving you more stability. Yes. So this is the final circuit, what we have as CS common source Cascode LNA with inductive degeneration, and this is one of the popular topology and widely used topology in many of the transceivers. Right. So with this, I am just winding up for today. So what is left with this topology is we need to verify the noise figure of this topology. So we need to study the noise sources and find out what is the noise figure of this. And after that, we will go back to the common gate topology. There also we will see a version of Cascode common gate. And with that, you will be prepared for doing the assignment. That is a design of a common gate LNA. Right. So I think you will get another after giving the assignment problem. By the time I'll be covering the sufficient theory part, you will get another 2 weeks of time to work on that. Right. So that's all for today. So if you have any questions, you can ask now.